Welcome to our deep dive into the fascinating world of signals in medical imaging. In this lecture, we'll explore the foundational concepts that every biomedical engineer needs to know. From point impulses to sinusoidal signals, we'll break down the building blocks of how information is represented, processed, and visualized in medical technology. Whether you're new to the field or brushing up on your knowledge, this journey will help you understand the critical role signals play in everything from MRI scans to digital X-rays. Let's get started by setting the stage for why signals matter so much in engineering and beyond. This course, BME 422 Medical Imaging, is designed to introduce you to the essential concepts of signals and systems. Led by Dr. Loay Alzube from the University of Mount Union, we'll cover everything from the basics of signal types to their mathematical representations. You'll learn how signals are used in medical imaging, why they're crucial for system design, and how they impact both hardware and software development. By the end of this lecture, you'll have a solid foundation for more advanced topics in biomedical engineering. Signals are a cornerstone of electrical and biomedical engineering. They're not just limited to engineering, though fields like business and finance also use signal processing concepts. Popular tools like MATLAB and Excel have built-in signal processing capabilities, making these concepts accessible to a wide range of professionals. In this course, we'll focus on the mathematical foundations, such as linearity and transformations, that underpin signal processing. Understanding these basics will help you appreciate the power and versatility of signals in modern technology. Medical imaging relies on a deep understanding of signals and systems. In this chapter, we'll explore how signals are represented, manipulated, and analyzed. You'll see how concepts like Fourier analysis and Laplace transforms are used to model and simulate complex systems. These mathematical tools allow engineers to design, test, and optimize medical imaging devices, ensuring accurate and reliable results for patients and clinicians alike. Signals are everywhere, from the voltages in a circuit to the pixels in an image. They form the backbone of modern engineering and technology. In medical imaging, signals help us capture, process, and interpret data from the human body. Whether it's an electrical signal from an ECG or the intensity variations in an MRI scan, understanding signals is key to unlocking the secrets of the body and improving healthcare outcomes. Signals come in many forms. Electrical signals like voltages and currents are common in circuits. Acoustic signals include audio and speech, while video signals represent intensity variations in images. Biological signals such as DNA sequences are also crucial in biomedical engineering. The internet has introduced new types of signals like multimedia streams. Noise or unwanted random components is always present and must be managed. Each type of signal has unique properties and challenges, making signal processing a diverse and dynamic field. Video signals are particularly interesting because they are discrete in several dimensions. An image has a specific horizontal and vertical resolution, like 320 x 240 pixels. It's also sampled over time, for example, at 30 frames per second. Each pixel is represented by a certain number of bits, often 8 to 24, to capture color information. Audio and video are often compressed to save space and bandwidth. Understanding how video signals are structured helps engineers design better imaging systems and compression algorithms. Signals can be visualized in different ways. One common method is a functional plot, where you graph the signal's amplitude over time or space. Another is an image display, which is especially useful for video and medical imaging. These visualizations help engineers and scientists understand the behavior of signals, identify patterns, and troubleshoot issues. Effective visualization is a critical skill in both research and practical application. Medical imaging, we often represent three-dimensional objects as two-dimensional images. A 3D object is made up of voxels, while a 2D image consists of pixels. For example, an MRI scan might show a slice through the body, converting complex 3D structures into a format that's easier to analyze and interpret. This process is fundamental to many imaging techniques, allowing us to visualize internal anatomy in a clear and meaningful way. Signals are defined by independent variables. Time is the most common, with xt representing a signal as a function of time. But signals can also depend on space, making them two- or three-dimensional. The relationship between the amplitude-dependent variable and the independent variable is what defines the signal. Different types of functions, continuous, discrete, or random, can be used to describe signals, each with its own set of properties and application. There are many types of functions that can describe signals. Continuous functions change smoothly over time or space, while discrete functions jump from one value to another. Random functions introduce unpredictability, which is common in biological and environmental signals. Understanding these different types of functions helps engineers choose the right tools and techniques for analyzing and processing signals in various applications. Most signals in the physical world are continuous time (CT) signals. These signals change smoothly and can take on any value at any instant. Examples include voltage, pressure, temperature, and velocity. To observe these signals, we often use transducers, devices that convert physical signals into electrical ones. Common transducers include microphones, voltmeters, and pressure sensors. Understanding CT signals is essential for designing systems that interact with the real world. Discrete time (DT) signals are represented by a sequence of numbers, each corresponding to a specific point in time. These signals are common in digital systems, such as computers and digital audio. Examples include MIDI codes, stock market prices, and digital images. Many properties of CT signals also apply to DT signals, making it possible to analyze and process both types using similar mathematical tools. Signals repeat themselves over time. These are called periodic signals. Continuous time periodic signals repeat every t seconds, while discrete time periodic signals repeat every n samples. The sum of two periodic signals is also periodic if their periods are rationally related. This property is fundamental in signal processing, especially when building complex signals from simpler ones, such as in Fourier series. Symmetry in signals makes them easier to analyze and understand. Signals with regular patterns, such as periodic signals, can be represented more simply using mathematical tools like the Fourier transform. This symmetry allows engineers to break down complex signals into fundamental components, making analysis and processing more efficient. Signals can be classified based on their energy and power. Energy signals have a finite total energy, while power signals have a finite average power over time. Some signals, like unstable ones, have unbounded energy or power and are not physically realizable. These concepts are closely related to familiar electrical measures like mean, standard deviation, and RMS value. Understanding energy and power helps engineers design efficient and stable systems. Summarize what we've learned so far. Signals are everywhere and they come in many forms: continuous, discrete, time-varying, and spatially varying. All signals can be described using mathematical abstractions like the Fourier transform. The more symmetry a signal has, the easier it is to work with. We've also introduced the concepts of energy and power signals, which are fundamental for understanding and designing real-world systems. Signal processing: we often represent complex signals using simple building blocks like sinuwaves and impulse functions. These fundamental components make it easier to analyze, approximate, and compress signals. For example, JPEG image compression uses these principles to reduce file size while preserving important details. Today, we'll explore some of these basic building blocks and learn how they're used in practice. Let's look at signals derived from the point impulse. The point impulse, or delta function, is a mathematical abstraction that represents a signal concentrated at a single point. By shifting or extending this impulse, we can create line impulses and sampling functions. These concepts are essential for understanding how signals are sampled and reconstructed in digital systems. Impulse function, also known as the direct delta or unit impulse, is a fundamental concept in signal processing. It's defined mathematically to be zero everywhere except at a single point, where it is infinitely high but has a total area of 1. In discrete time signals, the impulse is represented as a sequence with a single non-zero value. The impulse function is used to model sudden events and to analyze system responses. Unit step function is another basic signal, defined as 0 for negative time and 1 for positive time. It's the integral of the impulse function. The unit ramp function, in turn, is the integral of the unit step, increasing linearly over time. These functions are used to model systems that turn on or ramp up at a specific moment, making them essential tools in engineering analysis. Visualizing the unit step and ramp functions helps solidify your understanding. The step function jumps from 0 to 1 at a specific point, while the ramp function starts at 0 and increases steadily. These simple shapes are the foundation for more complex signal behaviors and are widely used in system modeling and analysis. Rect and sinc functions are important in signal processing. The rect function is a simple rectangular pulse, while the sinc function has a characteristic oscillating shape. These functions are used in sampling theory and filter design, helping engineers control how signals are shaped and reconstructed in digital systems. In discrete time systems, the unit step and ramp functions are constructed by summing sequences of pulses. The discrete time rectangular pulse is a time-limited version, useful for modeling digital signals. These building blocks are essential for understanding how digital systems process and manipulate information. Let's look at some visual examples of discrete time step and ramp functions. These plots show how the signals evolve over time, with each step or ramp corresponding to a specific sample. Visualizing these functions helps you understand how digital systems interpret and process signals. Here's another example of a discrete time signal, showing how a sequence of pulses can be combined to form more complex shapes. These examples illustrate the flexibility and power of digital signal processing, allowing engineers to create and manipulate signals with precision. Sinusoidal signals like s, x, y equals sin2 pi u 0x plus upsilon 0y are fundamental in signal processing. By varying the fundamental frequencies, you can create slow or fast oscillations in different directions. These signals are used to model periodic phenomena and are the basis for many signal processing techniques, including the Fourier transform. Sine and cosine functions are at the heart of signal processing. A sinusoid is a periodic signal, repeating every t equals 2 pi / omega seconds. The amplitude, frequency, and phase completely determine its behavior. Later, you'll learn how to decompose complex signals into sums of sines and cosines using the Fourier series, a powerful tool for analysis and synthesis. Signals can be shifted in time, either delayed or advanced. This is done by replacing xt with xt(t1) for a delay or xt plus t1 for an advance. The shifting property of the unit impulse allows us to isolate specific values of a signal, which is useful for analysis and system design. Time shifting is a basic operation that underlies many signal processing techniques. Continuous time signal is one that changes smoothly without jumps. However, some signals are only continuous in pieces, with sudden jumps at specific points. These are called piecewise continuous signals. The ramp function and sinusoid are examples of continuous signals, while a triangular pulse may be piecewise continuous. Understanding these distinctions is important for analyzing real-world signals. Let's look at a visual example of a piecewise continuous signal. These signals are continuous except at a finite number of points where they may jump abruptly. This property is common in real-world signals, especially those generated by switching systems or sudden events. Continuous time signal is differentiable at a point if its rate of change is well defined there. However, piecewise continuous signals may not be differentiable everywhere, they can have sharp jumps. In such cases we use the concept of a generalized derivative, which includes impulses at the points of discontinuity. This mathematical tool helps engineers analyze and model real-world signals with sudden changes. One of the most common ways to create discrete time signals is by sampling a continuous time signal. Samples are taken at regular intervals, converting a smooth signal into a sequence of numbers. The sampling interval determines the sample frequency. Proper sampling is crucial for accurately representing and reconstructing signals in digital systems. Here's a visual representation of sampling. The continuous signal is shown alongside its discrete samples, illustrating how information is captured at specific points in time. Uniform and non-uniform sampling are both possible, but uniform sampling is most common in digital systems. Later, you'll learn about the sampling theorem, which defines the conditions for perfect signal reconstruction. Representing signals using fundamental building blocks is a powerful abstraction. We've introduced 4 key signals: impulse, unit step, ramp, and sinuwave, along with their continuous and discrete versions. We also discussed timeshifting and the sifting property, as well as the concept of derivatives for continuous and discrete signals. These tools form the foundation for more advanced signal processing techniques. Let's take a closer look at the impulse function. In continuous time, it's an idealized spike with 0 width and infinite height, but a total area of 1. In discrete time, it's a sequence with a single non-zero value. The impulse function is used to test system responses and is central to the analysis of linear systems. Unit step and ramp functions are not just theoretical, they're used in real-world systems to model switches, ramps, and other behaviors. For example, a system that turns on at a specific time can be modeled with a unit step, while a system that ramps up gradually uses the ramp function. These simple models help engineers design and analyze complex systems. The rect and sinc functions play a key role in sampling theory. The rect function defines the shape of a pulse, while the sinc function describes how signals are reconstructed from samples. These functions are essential for designing filters and ensuring accurate signal processing in digital systems. Sinusoids are the building blocks of many signals. By combining sines and cosines of different frequencies, engineers can represent and analyze complex signals. This approach is the basis for the Fourier series and transform, which are used in everything from audio processing to image compression. Timeshifting is used in many practical applications such as echo generation, signal alignment, and system analysis. By delaying or advancing signals, engineers can synchronize systems, compensate for delays, and model real-world phenomena. Mastering timeshifting is essential for effective signal processing. Understanding the difference between continuous and discrete signals is crucial. Continuous signals are smooth and can be measured at any instant, while discrete signals are defined only at specific points. Most real-world signals are continuous, but digital systems require discrete representations. Learning how to convert between these forms is a key skill in engineering. Later in the course, you'll learn about the sampling theorem, which defines the conditions for perfect signal reconstruction. This theorem is foundational for digital signal processing, ensuring that continuous signals can be accurately represented and recovered from their samples. Stay tuned for a deeper exploration of this critical concept. To wrap up, we've covered the essential building blocks of signals in medical imaging. From impulses and steps to sinusoids and sampling, these concepts form the foundation for advanced topics in biomedical engineering. Understanding how signals are represented, processed, and analyzed will empower you to tackle real-world challenges in medical technology. In upcoming lectures, we'll dive deeper into each of these concepts, exploring their mathematical foundations and practical applications. You'll learn how to use these tools to design, simulate, and test medical imaging systems, preparing you for a successful career in biomedical engineering. Stay curious and keep exploring. Thank you for joining this introduction to signals in medical imaging. Review the key concepts, practice with examples, and prepare your questions for the next session. With a solid grasp of these fundamentals, you're well on your way to mastering the art and science of biomedical engineering. See you in the next lecture.